Hello again. Tonight is going to be a short one, really. Event Horizon thoughts. It's not about the movie Event Horizon, but it's about black holes, or a certain aspect of it, and something that I was reading in a scientific paper. As I said, this is going to be a short presentation to drive the concept for consideration, as opposed to getting lost in too much minutia. And also by it being short and having this title, maybe it'll affect the YouTube algorithms and give us some more views. So black holes, they exhibit high gravity. The Keck telescopes in Hawaii did observe them over, I think it was 20 plus years, and could actually see these stars orbiting the supermassive black hole at the center of the Milky Way galaxy. Couldn't see the black hole, could see the stars orbiting it. Black holes, gravity, not seen. I found out from reading an additional paper that they've actually been able to create photon-photon collisions in particle accelerators. You can't accelerate a photon. It goes at the speed of light. You might be able to, run it through some reflections and effectively slow it down, but it goes at the speed of light. But what you can do is if you have an energetic particle or an energetic atom, you can direct that with an accelerator. And at the point where a collision occurs, photons can be released. And if you release enough photons in a very, very small space, and the photons are of a certain high energy level, then the photons will actually collide. And there is actually a Feynman diagram. If you're into physics and particle physics and such, you know what a Feynman diagram is. And on the right, you see two photons coming in from the left, colliding, and the end result being these two arrows going out. You notice no wiggly lines going out. So two photons head-on colliding do not produce any other photons. They produce what is known as fermions, and it produces two of them. That's why they go off in different diagonal directions. It produces a fermion and anti-fermion. And in the presence of each other, particle and antiparticles of the same type tend to annihilate each other within a tiny fraction of a second. Two photons go in, they collide. Essentially, nothing comes out but pure energy, no photons. So if you were to collide two photons, you would get no photons out. Now, the way you do this is by creating enough of a flux of photons so they have nowhere else to go but to collide into one another. So you change the probability of being rare that two photon collisions occur, but by the flux, by the density of photons, you'll transition that to be a probability of one. So a photon collision will occur. And you can measure this as energy in, energy out of a system. You've got high gravity at black holes. You've got photon-photon collisions. And as usual, I connected the dots. So the current consideration is that when a photon passes beyond the event horizon of a black hole, it never exits. It never produces any other photons. Photons go in, they don't come out. Purportedly, the high gravity of a black hole disallows sufficient velocity at the speed of light for the photons to leave the black hole. Not quite buying that, but it makes some sense that if you can get a threshold up high enough where it's beyond the speed of light, then things moving at the speed of light will never come out. If time is stretched, even if they're moving at the speed of light, they'll never come out. Stephen Hawking had this postulation that there's a thing called Hawking radiation that we have not yet observed, is a means by which radiation can slowly leak out over time from a black hole, such that a black hole over a very long period of time would dissolve. The fact that you have radiation, a photon coming out of a black hole, that kind of breaks the whole too much gravity for photons to escape. If you listen to the people discuss Hawking radiation, you'll actually see that originally Hawking did not postulate that there would be Hawking radiation. Later on, out of kind of nowhere, he said, this has to exist, otherwise you have information destruction. What that really means is photons are a thing. They go into the black hole, they never come back out. That's the destruction of those photons. It doesn't transition into other energy. It's gone. Given all the conservation mechanisms in physics, that just didn't fly right. So he postulated that there should be radiation coming out of black holes and very low energy particles, very slow over time. And that way black holes could dissolve. So I thought
More,
it was,
it's not just photons because of quantum instabilities, like right now at this moment between you and the computer, that is like particles, they're pop in and out of existence. So they pop in, they are the opposite, so they annihilate itself and cease to exist. So when those happen in the edge of the event horizon, sometimes one of the pairs go inside and the other pairs go outside, and then that actually makes real mass, and that's what actually evaporates and and that's what causes the evaporation of the black hole.
But even when he postulated it, he said, we do not currently have the technology to observe such energy levels. We have, as of yet, no observational confirmation of Hawking radiation. Okay, so here's the concept that I'm going to put forth. If you think about the gravity of a black hole and you think about photon-photon collisions not producing photons, then you can have a solution whereby photons can enter a high gravity, high density environment. And if they collide with one another to a complete consumption scale, you'll have photons going in, never coming out, not even other photons come out. Neutron stars have high gravity. They have sufficient gravity to tear down atoms into their composite neutrons, basically splitting protons. Neutrons are not acceleratable by magnetic fields. They're accelerated by gravitational fields. So that makes the neutron star compress tighter and tighter, and stripping things down below the level of a neutron, you get a variety of flavors of quarks, up and down quarks initially, but there is postulation that says if it compresses further, you can get strange quarks. As the gravity attains a certain threshold, you go from having a neutron star to a black hole. If you have a photon-photon collision that doesn't emit any photons, you now have a way of saying the photons go in, but they don't come out, and it's unrelated to the speed of light as an escape velocity. Particle annihilation. Given this annihilation, there would be no limit as to how much a black hole might be able to consume, because the particles get annihilated. You have anti-particle pairs that annihilate. Things go in, don't come out, which is what we do observe. So I said this was going to be short, so I've put forth a concept. Let's see how the public internet and comments respond to it. If you have photons passing through the event horizon of a black hole and not being emitted, it could be due to photon-photon collisions, annihilating particle and anti-particle pairs, and therefore no photons escape, and you won't even get high energy photons out. And it's unrelated to the speed of light as an escape velocity. So the next question becomes, how do black holes get so much gravity? And, well beyond neutron stars, they're conceptualized into their quark flavors of up, down, and strange. Maybe if you take that to the next level up, there's a gap between neutron stars and black holes at the energy level, and the gap is roughly the same distance up the energy chain as top quarks. So if you can have quark stars from neutron stars, they use up and down and strange. If you take the energy level up even higher, you can get quark star. But that's already a different presentation on the Broward Astronomy YouTube site, and you can go look at that one because I provide links as usual. So I provided a link to the Keck observations based upon the observing of the positions of stars as they go around the center of the Milky Way due to the black hole. They animated that, and that's the YouTube video you see there. And then if you're unfamiliar with, I didn't think a photon could ever hit another photon. Not without particle accelerators and a lot of effort. So you can learn about the two-photon physics. And then if you're not familiar with Hawking radiation, there's that. And then the prior video on are black holes merely top quark stars? Okay, so what do you think? I know it's a bunch of gobbledygook that you don't completely understand, and that's fine. Any thoughts?
It's sweet and short, and it's good because it's gonna drive a little bit more people coming and watching the videos.
Well, that was the whole idea: is keep it short, make the concept items just bullet points and hyperlinks, and people can go off and explore it on their own, and then come back and provide me with comments
and ideas. Okay, so hold on a minute. Let's see if you can use this one. All right, Monroe, it's time to say at least that people like this video, want to comment or give an ideas. And please don't forget to like and subscribe.
Yes.
Like that one?
I don't monetize the Broward Astronomy YouTube channel. As somebody else on YouTube says, I'm just in it for the likes and the subscribes. Anything else before I stop recording?
Yeah, okay.
Stopping recording.